Okay, so in this video, I'll explain to you how to give the DFA that is equivalent to a given NFA. So if you, for example, had the following NFA given in an exam, and you were asked to give the equivalent DFA, what you would need to do is, first of all, determine what are the states that start at the beginning. So the start state always starts at the beginning. So for this case, it is 1, but also because we have the empty string here, which immediately creates a sibling branch for 3, in this case, the starting computation will be 1 and also 3. So that's why the start state would be the state 1 and 3. Then we produce the power set for all the states in Q. And so we would have phi 1, 2, 3, 1 and 2, 1 and 3, 2 and 3, and also 1, 2, 3. So this is known as the power set. This will definitely give us all the sets needed for the production of the DFA. And then we have the accept states. So the accept states would be any state with an accept state in it. So here we only have 1 as an accept state. So we just go to each one of these and say, okay, 1, this set has 1, so this is an accept state. This set has also 1, so it's an accept state. This has an accept state 1, so it's an accept state. And this has an accept state 1, so it's also an accept state. So each the set in the power set that has any one of the accept states would also be an accept state. So now starts the production. So here we have the production of each one of these states. So you see here, this is the power states. So each one of these sets in the power set would have its individual state. Right, so here we have phi, the set 1, the set 2, the set 1 and 2, the set 3, the set 1 and 3, the set 2 and 3, and the set 1, 2, 3. And obviously we have the start state, which is 1, 3, as we described earlier. Here we described that the start state is 1 and 3 because we start at 1, but then 3 is produced immediately. So we have 1 and 3 at the beginning. And then here we have the power set, which is mapped to each one of these. So we draw these before we draw any of the transitions. Okay, and then we also decide the accept states, which is all the states that have any one of the accept states in the original NFA. So the original NFA has only 1 as an accept state. So for the states in the DFA, any state in one of the sets in the power set would result in that set being a accept state. So you can see, because this one has 1, this one has 1, this one has 1, this one has 1. So all of these in here are considered an accept state because they have 1 in them, and 1 is an accept state, which makes them also an accept state. So this is the start state 1 and 3, and these are the accept states. So now we start drawing the transitions based on the union function. So what we're going to do is we are going to have we're going to start one at a time. So you're going to go to, for example, 1, and you're going to see where does 1 go given A. So if you give 1 A, it goes nowhere. So that's why with 1, you go to phi. Okay, so then you come here. If you give 1b, where does it go? It goes to 2. So you see here that if you give 1, B, it goes to 2. Okay, so now we're going to go to 2. Now, what are the options that we have? The options that we have are always the alphabet. So the alphabet is A and B. So we're going to explore A and B. So if we have 2 and we give 2B, so what's going to happen? It's going to go to 3. And if we give 2A, it's going to go to 2 itself, and also it's going to go to 3. So you can see here that if you give 2B, it's going to go to 3, but if you give 2A, it's going to go to 2 and 3, right? So 2 goes back with A back to itself to 2 and also goes to 3. So if you give the state 2, A, it will go to 2 and it will also go to 3. And you can see here 2 going with A, going to 2 and 3. So you go also to here 1 and 2. So how do you solve when you have more than 1? So what you're going to do is you're going to see, so if I give 1 A, where does it go? It goes to phi. What if I give 1 B? Where does it go? It goes to 2. Okay, so now with 1, if I give it B, it's going to go to 2, and if I give it A, it's going to go to phi. So that is now the set for 1. So now let's see the set for 2. So the set for 2 would be, what if I gave it A? So for 1, A is nothing. For 2, A is 2 and 3. So you can see here that now, because for 1, A is nothing, and for 2, giving A goes to 2 and 3, so that's why the entire set is the union of phi with 2 and 3, which results in 2 and 3, because nothing united with 2 and 3 gives you 2 and 3. So now we look at 1 with B. 1 with B goes to 2, so we have that on the side, which is 2. Okay, so now what about 2? 2 with B goes to 3. So 1 goes to 2 with B, and 2 goes to 3 with B. So the union of 2 and 3 is where 1 and 2 go together to B. So 1 and 2 with A go to 2 and 3, and 1 and 2 with B go to 2 and 3. And the way that we do it is that we see, where does 1 go? Where does 2 go, given the alphabet? And then we take that union of wherever both of them go, and then we produce the transition output. So now let's see here, for example, 2 and 3. What happens with 2 and 3? So what would happen here is that we have 2. So we'll see, where does 2 go with A? It goes to 2 and 3. Okay, so where does 3 go to given A? It goes to 1 and also back to 3. So which means that 2 goes to 2 and 3, and 3 given A goes to 1 and 3. So the union of 2 and 3 and 1 and 3, the union of 2 and 3 and 1 and 3 is 1, 2, 3. So that's why you see here that 2 and 3 together, given A, goes to 1, 2, 3. So you follow that methodology for everything, and then you get this one. Obviously, phi has no state phi here, so given A and B is just going to go back to itself. Now you start looking at all of the transitions that only have things coming out of it. Even if it had a one going back into it, but it doesn't have any other state going into it, then you get rid of it. So you can see here this one has only one thing coming out of it. This one has two coming out of it, nothing going into it, nothing going into it. So we just remove them, and then we are left with this. And that is the